Preparing for a systems engineering at Cloudflare interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain Cloudflare's edge architecture and the role of Anycast? Cloudflare's edge network uses Anycast BGP to steer clients toward nearby points of presence. Each POP terminates traffic, applies security policies, and serves cached content or forwards requests. I would combine health checks, routing advertisements, capacity controls, and graceful withdrawal when a site fails. Anycast improves latency and absorbs attacks, but routing can shift abruptly, so local overload protection and origin failover remain essential for resilience. While answering, cover points of presence, Anycast BGP advertisements, latency reduction, traffic steering, health checks, capacity management, origin protection, and failure behavior when a location becomes unavailable. Question 2. Walk me through what happens when a client resolves a domain through Cloudflare DNS. A client typically asks a recursive resolver, which queries Cloudflare's authoritative nameservers if its cache is stale. Cloudflare returns the relevant record, honors TTL policy, and may provide DNS-SEC authentication. Its Anycast nameservers let queries reach a nearby healthy location. I would monitor latency, error rates, and propagation behavior, while remembering that low TTLs improve agility but increase query load and operational cost. Make sure to cover recursive versus authoritative resolution, DNS records, caching and TTLs, Anycast nameservers, negative caching, DNS-SEC, failover, and how operational changes propagate safely across a globally distributed service. Question 3. How would you design a globally distributed DDoS mitigation system? The system should detect attacks close to ingress, absorb volumetric traffic across many Anycast locations, and apply increasingly specific mitigations. I would use baseline models, signatures, connection limits, and per-customer policies, with a fast control plane distributing rules. Mitigations must be fail-safe, observable, and reversible. The key trade-off is blocking aggressively enough to protect capacity without harming legitimate users during flash crowds or unusual events. In your answer, discuss volumetric, protocol, and application attacks, Anycast absorption, hierarchical detection, rate limiting, scrubbing, false positives, control plane safety, and preserving availability for legitimate traffic. Question 4. How would you design a rate limiter for Cloudflare's edge? I would start with a token bucket keyed by customer, API key, IP, or route. Tokens refill at a configured rate, allowing controlled bursts while enforcing a long-term limit. At global scale, exact shared counters are expensive, so I would use regional ownership, replicated approximate counts, or a centralized fast store depending on accuracy needs. For availability, bounded fail-open behavior may be safer for low-risk traffic, with strong observability. Be sure to mention token bucket or leaky bucket algorithms, distributed state, identity keys, burst handling, synchronization costs, fail-open versus fail-closed behavior, and protecting both customers and shared edge capacity. Question 5. What caching strategy would you use for Cloudflare's CDN? I would derive a precise cache key from scheme, host, path, and approved query parameters, then honor cache control and surrogate control policies. Fresh objects serve immediately. Stale objects can be revalidated with e-tags or last modified. To prevent stampedes, one request refreshes while others reuse stale data briefly. Tiered caching reduces origin traffic, while purge APIs handle urgent changes. The central trade-off is performance versus freshness and invalidation complexity. Focus on cache keys, freshness, revalidation, purge mechanisms, cache control semantics, negative caching, stampede prevention, personalized content, tiered caching, and balancing origin load against content correctness. Question 6. How would you investigate a sudden increase in latency at one Cloudflare point of presence? I would first confirm whether latency affects all traffic or a specific protocol, customer, route, or machine pool. Then I would compare CPU, memory, queues, packet drops, disk, upstream latency, and connection counts with neighboring POPs. Traces and recent deployment data help isolate the path. I would drain unhealthy capacity or roll back a correlated change, while preserving samples and timelines for root cause analysis. In your answer, describe metric segmentation, request path tracing, host and process checks, saturation signals, recent changes, network dependencies, comparison with neighboring POPs, rollback decisions, and customer impact assessment. Question 7. Explain how you would design a reliable configuration distribution system for edge servers. I would store immutable, versioned configurations and validate them before publication. Agents fetch or receive a signed version, verify compatibility, write it locally, and activate it atomically. Rollouts should progress by percentage or region, with health gates and automatic rollback. Agents need idempotent reconciliation and a last known good configuration when disconnected. This favors eventual consistency with strong safety guarantees over instant global convergence. Cover versioned configuration, validation, staged rollout, atomic activation, acknowledgements, rollback, regional fanout, idempotency, consistency expectations, and behavior when agents lose connectivity to the control plane. Question 8. What Linux performance signals would you inspect when an edge proxy is overloaded? I would correlate application latency with CPU utilization, run queue depth, memory pressure, page faults, file descriptor usage, and socket states. For networking, I would inspect retransmissions, drops, software consumption, and interface saturation. Tools such as PIDstat, VMSTAT, SS, SAR, perf, and eBPF can reveal where time is spent. I would avoid treating high CPU alone as the cause. Queuing and kernel limits often explain the user visible delay. Mention CPU saturation, run queues, memory pressure, page faults, file descriptors, socket states, retransmissions, softworks, disk latency, cgroup limits, and separating application bottlenecks from kernel or network constraints. Question 9. How would you troubleshoot packet loss between an edge location and an origin? I would compare loss by destination, interface, protocol, and time window, then inspect counters, retransmissions, congestion, MTU behavior, and route changes. Packet captures can distinguish dropped packets from delayed acknowledgements, while application logs reveal whether the origin is slow rather than unreachable. I would test an alternate path or upstream and check neighboring POPs. Remediation might involve routing changes, capacity relief, MTU correction, or origin failover. Discuss scope isolation, interface counters, routing, MTU, congestion, TCP retransmissions, traceroute limitations, packet captures, origin health, alternate paths, and distinguishing network loss from application timeouts. Question 10. How would you design a service that maintains availability during a regional outage? I would separate failure domains and keep request processing as stateless as possible. Health checks would withdraw unhealthy regions from routing, while spare capacity in healthy regions absorbs redirected traffic. Stateful data needs replicated, clearly defined consistency guarantees, and clients should tolerate retries or degraded features. Origin failover must avoid retry storms. I would validate the design with regional blackouts, capacity tests, and regular game days. Be sure to cover failure domains, Anycast or global routing, health-based withdrawal, stateless processing, replicated state, degraded modes, origin failover, capacity headroom, and testing through controlled fault injection. Question 11. What are the main challenges of running QUIC and HTTP 3 at the edge? QUIC runs over UDP and integrates TLS 1.3, reducing handshake latency while providing stream multiplexing without TCP head-of-line blocking. The edge must enforce amplification limits, handle connection migration, and expose useful packet-level metrics despite encrypted transport. I would retain graceful HTTP, 2 or TCP fallback because some networks block or mishandle UDP. QUIC can improve mobile performance, but its operational tooling and CPU profile require deliberate investment. Cover UDP handling, connection migration, TLS 1.3, packet loss recovery, amplification limits, observability, fallback to TCP, middlebox behavior, CPU cost, and comparing performance under different network conditions. Question 12. How would you prevent a cache stampede when a popular object expires? When a hot object expires, I would allow one request to refresh it while concurrent requests receive the previous value or wait briefly. A per-key lock, stale while revalidate, and randomized expiration reduce synchronized origin requests. I would bound refresh timeouts and preserve stale content during temporary origin failures. The lock must be scoped carefully so one problematic object does not serialize unrelated traffic or create a new bottleneck. In your answer, explain request coalescing, stale while revalidate, jittered expiration, locking scope, negative caching, origin protection, timeout handling, and ensuring one slow refresh does not block every client. Question 13. How would you build observability for a globally distributed proxy service? I would define SLOs for availability, latency, error rate, and cache performance, then emit metrics by region, protocol, route, and customer class. Structured logs support forensic analysis, while sampled traces connect edge work to origin calls. High cardinality labels need controls to prevent telemetry overload. Alerts should detect user impact rather than noisy internal fluctuations, and dashboards must distinguish regional failures from global regressions. Mention metrics, structured logs, distributed traces, high cardinality controls, exemplars, regional dimensions, SLOs, alert design, sampling, privacy, and correlating edge observations with origin and customer impact. Question 14. How would you safely roll out a new network-facing proxy release? I would validate the binary with unit, integration, protocol, and load tests, then deploy it to a small canary slice. Shadow traffic can expose behavior differences without affecting responses. Automated gates should monitor errors, latency, saturation, connection failures, and customer-specific regressions. I would expand gradually by machine and region, keep rollback one command away, and separate code rollout from feature activation through flags. Focus on compatibility, canaries, automated health gates, traffic shadowing, rollback speed, feature flags, protocol coverage, resource regression detection, and preserving a known good binary and configuration. Question 15. How would you choose between strong and eventual consistency for an edge configuration service? I would classify data by consequence. A certificate revocation or security rule may require strongly ordered activation, while analytics or cache metadata can converge eventually. For eventual data, version numbers, timestamps, idempotent updates, and conflict policies prevent ambiguity. Strong consistency costs latency and availability during partitions, so I would reserve it for safety-critical paths. Every service should define a safe stale or disconnected behavior explicitly. Discuss configuration types, user visible risk, propagation delay, quorum or leader costs, versioning, conflict resolution, stale reads, fail-safe defaults, and whether temporary inconsistency can create security or availability problems. Question 16. How would you diagnose memory leaks in a long-running systems service? I would confirm growth in resident memory and distinguish a leak from legitimate cache expansion, fragmentation, or kernel buffers. Heap profiles, allocation tracing, object retention analysis, and file descriptor counts help identify the owner. I would correlate growth with request types and deployment versions, then limit damage with recycling or bounded caches. After fixing ownership or cleanup, I would run a prolonged production-like test and compare steady-state behavior. Cover reproducibility, resident versus virtual memory, allocation profiling, heap snapshots, object lifetimes, caches, fragmentation, file descriptors, traffic correlation, stage mitigation, and verifying that a fix survives realistic workloads. Question 17. What security controls should protect an edge service and its control plane? I would isolate the control plane, require mutual authentication, and grant services only the permissions they need. Configuration and binaries should be signed, verified, and delivered through an auditable pipeline. Secrets belong in a managed store with rotation and short-lived credentials. Edge processes need sandboxing, secure defaults, resource limits, and comprehensive audit logs. I would also rate limit administrative APIs and make emergency changes reversible. Be sure to mention least privilege, mutual authentication, signed artifacts, secrets management, isolation, secure defaults, audit logs, rate limits, supply chain validation, and separate control plane access from customer traffic. Question 18. How would you design backpressure for an edge proxy receiving more traffic than it can process? I would keep queues bounded and reject or shed work before memory and latency become unbounded. Admission control can prioritize authenticated or critical traffic, while connection and request limits protect workers. Short, carefully chosen timeouts prevent resource retention, and circuit breakers stop repeated calls to failing origins. I would avoid broad retries during overload because they multiply traffic. Backpressure should surface clear metrics and predictable client errors. Discuss bounded queues, admission control, connection limits, load shedding, prioritization, timeouts, retries, circuit breakers, overload signaling, and protecting critical traffic without allowing queues to hide saturation. Question 19. How would you design an efficient log and telemetry pipeline for Cloudflare-scale traffic? Request handling should never synchronously depend on the telemetry backend. I would emit structured events into local bounded buffers, batch and compress them, then ship asynchronously with retry and backpressure policies. Sampling can preserve detailed data for errors while reducing routine volume. Schemas need versioning, and sensitive fields require filtering or aggregation. If the pipeline is unhealthy, telemetry should degrade or drop safely rather than consume proxy resources. Cover local buffering, batching, compression, sampling, backpressure, schema evolution, partitioning, privacy, delivery guarantees, cost controls, and preventing observability failures from affecting request processing. Question 20. Tell me about a systems incident you handled and how you would improve the service afterward. I would structure the story around impact, timeline, actions, and learning. For example, after a deployment caused elevated origin errors, I would show how dashboards detected the regression, how traffic was drained and the release rolled back, and how customer communication remained timely. The postmortem would identify technical and process contributors, then assign measurable fixes such as safer canaries, stronger tests, and a new alert. Blameless analysis improves reliability. In your answer, use a clear timeline: customer impact, detection, diagnosis, mitigation, communication, root cause, contributing factors, measurable follow-up actions, and blameless learning rather than individual fault. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.